Good morning and welcome back, everybody. Yeah, good morning, Mr. Bailey. I don't want to be here. Let me go back to spring break. I hope your spring break was okay, right? I hope you did find some time to get some rest or relaxation or whatever it is you wanted to do, but I trust it was full of catching up on everything. I had a good spring break, and now I'm finding it hard to get back into the swing of things, but you know. We'll get there. We'll get there. For show of hands, how many of you this is your first class back from spring break? Oh, geez. Okay. All right. I got to break you in slow then. I prepared some questions for my physics 2B students, but I will just you know, you do get a little bit rusty, right? Sometimes. And it's just, you know, coming back into it can be pretty hard. So here's some questions to just warm up, right, the brain and get it going. Anybody have any questions here? Are we good? Right. How many points is the quiz? Right. Okay. Okay. So these get harder as we go, right? Any questions? Yeah. Okay. Right. Right. All right. This one's hard. My physics 2B students were like, wait a second. If this is defense against the dark arts, then what class is the dark arts? And I immediately said chemistry. So yeah, there we go. Right. And then finally, probably the hardest question of all. Okay, this was a test of your movie knowledge, and I think one person got it. Okay, so this is a line from a movie. Does anybody know what the movie is? Monty Python Search for the Holy Grail. One of these days, okay, you know what? I'm going to go over and teach movie appreciation or music appreciation, whatever it is they teach over there, because they're teaching the wrong stuff. They probably made you watch like The Godfather and stuff like that. But, you know, you got to get the right movies in there. All right. So, where were we? For realsies now. I had to go back and check YouTube. Right? If it hadn't been for my YouTube recording, I'm not sure I would have remembered. But we were transitioning away from simple harmonic motion into waves. Right? And figuring out ways to talk about waves, both mathematically and in concept. And we're going to push forward with that, only we're going to spend pretty much the rest of the unit talking about waves in two different categories. We're going to talk about waves on strings and waves in air. And so this is going to talk a lot about sound waves and how we hear and things like that. We'll get into that a little bit more today. But I wanted to point out something that I dropped before, but bear repeating, and we'll need to do a little demonstration here of what's going on. There's more than two kinds of waves out there, but we're going to concern ourselves with the two primary kinds, which are transverse and longitudinal waves. I need a volunteer, somebody else that can hold the other end. Very long, very thin, slinky. There you go. You volunteer for everything.
It makes it go faster.
It does, right? You get out of here sooner, less pain. Yeah, okay, all right. So let's hold this up so everybody can see. All right, so what I'm gonna do is I'm gonna put a transverse wave pulse on this slinky, okay? And that's gonna involve me pulling it down, right? And do you see how that pulse that happens there, okay? The wave is going back and forth horizontally, but the way that I pulse it, I can pulse it a little bit like this, right? The wiggle is going up and down, right? But the wave is traveling side to side. Okay, now we try to calm this down just a little bit. All right, let's hold it up so we can see. All right, now I'm going to do a longitudinal pulse when it stops wiggling. Okay, here we go. Longitudinal pulse. Do you see what that one did? Okay, it's not here. The wiggle. Okay, in this case, a compression is acting along the same axis as the direction that the wave is traveling. I'm not very good at this, right? But I'm giving a little bit. But you can see that compression moving back and forth in the slinky. Thank you very much. Just set it on the ground like that. Thank you. So, transverse waves, right? You got the wiggle is going perpendicular to the direction that the wave is traveling. And then a longitudinal wave has the wiggle, so to speak, the compression, okay, is traveling along the same direction that the wave is traveling. Now, you might be like, well, so what, Mr. Balogh? Why is that important? Well, it all has to do with the material that waves travel through. When waves are traveling in solids, and also a rare exception would be water waves traveling on the surface of water, those are transverse waves. Actually, the water waves are circular ones, but you didn't want to know that one. Longitudinal waves can travel through any medium, as long as there is a medium. The one place sound waves can't be is space. Transverse waves really can only travel in solids. And so it's important that we understand the kind of wave that we have when we are talking about sound waves in particular. So waves on a string, they can be transverse, they can be longitudinal, they can be any kind of thing, because that's a solid material. But what kind of material is air? Solid, liquid, gas. It's a gas, right? Hopefully, right? And in fluids, so in physics, we say a fluid that's both a liquid and a gas. It's just something that's not solid. In fluids, waves can only travel longitudinally. And we can kind of do that experiment here, right? If I grab an air molecule, that one right there, got it, okay? And I pull this air molecule down from the place where it was when it started. Okay, I want everybody to watch. What happens when I let go? Did it spring back to its original position? Was there any reason for that air molecule to go back to where it was? No. There's no restoring mechanism in fluids for bringing particles back to their original positions. Unlike in solids, right, where the parts are all connected to each other, and if I pull this up, right, it wants to come back to where it was before. So transverse waves can only exist in mediums that have that restoring force. Longitudinal waves exist everywhere else, because you can take any material and compress it, and it will try to push back. Right? All right, wave speed. The speed of a wave depends on the... You've already forgotten the whole spring rate, right? Okay. The medium, right? Speed of a wave depends on the material, the medium in which that wave is traveling. And while it's, again, true, this statement, this equation that we talked about last time, right? That wave speed, wavelength, and frequency are related to each other. You can only change the speed if you alter the properties of the medium. So for a wave on a string, its speed, and I think I maybe already said this, its speed is going to be governed by the tension in that string divided by the mass per length of that string. The symbols we use for this are T for tension and mu for mass per unit length, where u is equal to the mass of the string divided by its length. So that's the speed of a wave on a string, a rope, a chain, really any kind of solid material. And again, the speed depends on the medium, depends on how tight that medium is. If we change the tension, we're going to change the speed of the wave. And it depends on how thick or heavy that medium is. And how many of you in here play a stringed instrument like guitar, violin, viola, something like that, right? Okay. When you're tuning your instrument, right, you're changing the tension. What happens if you tighten on that tuning peg for the frequency of the string? Yeah, sound change goes up, doesn't it? You tighten it, it goes up, and as you loosen it, it goes down, right? What we're doing is we're changing the tension in that guitar string, which changes the speed, which alters the frequency or the pitch that we hear. And on a guitar or a violin or any other stringed instrument, the lower notes are sounding on thicker strings. They have more mass to their length. And so as that number gets bigger in the denominator, the wave speed goes down and the frequency goes down. So the material, the properties of the medium determine how fast the wave travels. Well, that's for waves on strings. What about waves in air? Or really waves, we'll just call them sound waves as a catch-all term for any wave that's traveling through a medium, right? And mostly air that we're used to, but it can be water, it can be other gases, all kinds of stuff. Now, your book has one equation for this, and I don't like it because it takes us back to the chapters we skipped over. So let me give you a different one that is more generally applicable. This pretty much will work everywhere, okay? So you will nearly always be given the speed of sound. Very rarely will we ask you to calculate the speed of sound based on the temperature. But I just wanted to point out here that sound, the speed at which sound waves travel through air, depends on the temperature. Change the temperature of it. Like what happens when you heat up air? Does it become more or less dense? Because less dense, it kind of tends to go up, doesn't it? Colder air is more dense. And so by changing the density, you're changing the pressure and the speed at which sound waves are going to travel is going to change. At 273 Kelvin, and I know we haven't done thermodynamics yet, okay, but Kelvin temperature scale is like Celsius. We just argue about where 0 is. 273 Kelvin is 0 degrees Celsius, which is 32 degrees Fahrenheit, so the freezing point of water. At 273, the speed of sound is 331. If you're not told what the speed of sound is in a problem, assume it's 343. Because that's the number you get at quote unquote room temperature. Chemists hate it when we say that, okay? It's standard temperature and pressure, okay? So if you're not told, 343 is the number you're going to use. You can use 340. You'll see some books and some sources, if you're watching YouTube or something like that, they'll say the speed is 340. It's just a sig figure thing. Okay? So it's 343 meters per second. And again, this is kind of more definitional. You're not really, hopefully, you probably need to calculate the speed of a wave on a string. We'll do that actually in lab. But speed of sound, more or less 343, unless you are told otherwise. That brings up a reminder. Tomorrow's lab, one second, come on. Tomorrow's lab is lecture. That was built into the schedule from the beginning of the semester, right? But just need time to catch up and get chapter 17 because what's happening next Thursday? Exam, okay? So we will lecture tomorrow, we'll lecture Thursday, we'll review on Tuesday, we'll do a lab on Wednesday, and then we'll be there. Juan?
Why is the mass of the length represented as mu?
Right? And why is T both tension and temperature? It's because there's only 26 letters in the alphabet, right? And you're in the part of physics where we start recycling symbols, right? Because mu, you're like, friction, and it's not. I so want to use like Chinese or something. Right, where we use ideograms to represent things because we've got a near infinite number of ways to do that. Anyway, I'm not in charge. I am part of the problem though because I perpetuate the symbology, right? But it's been that way for time immemorial. And though that's not a good excuse for doing anything, it does lead to consistency when you're studying things. Again, context is important, right? When you see a mu talking about waves, it's not friction, it's more or less mass per unit length. Right? In case you ever wanted to know the speed of sound in methyl alcohol, you can go look it up, right? Okay. But again, just sort of underscoring this idea that if you change the medium, you change the speed of a wave, right? It's not wavelength and frequency that change the speed of a wave. It's the material that it is in. And as you can see here, right, speeds tend to go up the lighter the gas, or it's hard to know kind of what the densities of these things are, but the density goes down for those. Anyway, more importantly for us, okay, we need to talk about how we are going to talk about sound waves, because quite frankly, it can get a little bit messy if we have, so first of all, a sound wave is a longitudinal wave because it's traveling in a fluid. That means that as I speak, right, and the vibrations that come out of my face, they're compressing air, and that compression is like traveling towards you like this, really, really fast, right? How do you draw a longitude? I mean, like, I can draw a transverse wave. That one's easy, right? Okay. Done, right? Okay, can be moving back, right? But how do you draw a I mean, it doesn't work, right? So it's just awkward. What does that mean? Is it Morse code? Like, what the heck is going on here? So what we're going to do is we're going to kind of dispense from the wiggle for just a little bit, and we're going to talk about sound waves traveling in just directions. So when I speak, the sound just doesn't come out of my mouth directly to you, right? You're not the only person that can hear me in the room. The sound spreads out from my source, right? This point source that's emitting vibrations into the air. And it spreads out, and we're going to model that as a spherical spreading out. And so now we're in 3 dimensions all of a sudden, right, as we're spreading this sound out into 3 dimensions. And the way we're going to talk about the direction a wave is traveling is we're using these rays. Those rays are basically like if you drew a line, okay, don't panic, it is not a vector. I mean, I know it's got an arrowhead on it, but it's not a vector, okay, right? It's simply indicating the direction that a wave is traveling. And so if I want to talk about how sound comes out of my mouth, it radiates out from this source, right? And I can draw rays that indicate, right, all of those directions that it travels.
The velocity is supposed to indicate the direction?
Yeah, it's just, there's no magnitude associated with this thing. We usually just draw from the source moving outwards, right? So we could draw a picture that like a speaker, right? Here's the source, and the sound is coming out in all directions, right? Technically, we'd have to draw like wiggles going it just gets messy. So we don't bother drawing the wiggles, we draw the rays. What we do think about though, and you'll see this in some of the diagrams, they'll do like concentric circles around the source, indicating the sound waves propagating outwards. Those are like the peaks, right? And so we could actually look at the peak-to-peak distance between those 2 wave fronts, right, as the sound waves travel. So you'll see both rays and you'll see these wave fronts as they're coming out. But we are now going to go into an area that I have little to no expertise in, and that is anatomy and physiology. Okay, so this is where you need to correct me, right? If you know anatomy and physiology, and I start getting some of this stuff wrong. But what do we call these flappy things on the sides of our heads? We call them ears, but that's not what our ear is. Our ear, right, is really the stuff that's inside of our head. What are these flappy things for? Make me look geeky. Protection? I mean, I don't know about you, but do you ever like catch your ear on something? It's not protected. It hurts. Let's do an experiment, okay? What I want you to do is I want you to take both of your hands and I want you to cup them behind your ears like this, like make a good kind of seal behind your ears. And what I'm gonna do is I'm gonna try to keep up a monotone, constant stream of talking while you take your hands off your ears and back on your ears. And just move them back and forth as I speak up here and try to say things while you do an experiment. And see if you can't tell the difference between having your hands behind your ears and not behind your ears. What did you experience?
You were louder.
I was louder. Could I get any louder? Why, yes. Right? So now I want you to do a very similar experiment, but we're going to kind of do it in reverse. And I'm not, don't do this, right? Okay? But what I want you to do is I want you to take your finger and I want you to pin your ear back to the side of your head. Like try to flatten it out a little bit. And again, I'm going to try to keep up that same monotone, and I want you to pin your ears and then let them go, and then pin your ears and see if you can't tell the difference in sound between when you have your ears pinned and when you don't have your ears pinned. And please do it quickly because I'm running out of breath. What did you experience? What did it sound like when your ears were pinned back?
Volume down.
Kind of volume down, but something else happened too.
Less bass.
Yeah, it got muddier, like high frequencies left and low frequencies left, and some people talk about how it feels like I was wearing earmuffs or something, right? Okay? So those experiments right there should clue you in as to what these flappy things are supposed to do. What do?
Pick up sound.
They collect stuff, right? Dirt and bugs. No, sound waves, right? Sound waves traveling through the air get captured and funneled down into your ear canal, right? And the ear canal's job is to take those sound waves and focus it down on the eardrum. According to the American Medical Association, what is the acceptable size of object to put into your ear if you are not a doctor going and looking for a problem? Well, no. There is a certain sized object that you're allowed to put inside of your ear. This is straight out of the manual for doctors. The allowable object is anything bigger than your elbow.
What point of the elbow?
I had a lot of questions when I read that. Okay? Right? Chief among them is, what experiences have doctors had? Right? Like, can you imagine all the things that kids have put into their ears and their nostrils? Right? The doctors have had to go in and take out, right? And like, it's oddly specific, isn't it? Right? It's like the size of your elbow. This part, right? And bigger, you're allowed to stick in your ear. Well, don't try this at home, but you can't put things that big inside of your ear, right? And that's pretty much the point of the guideline. Right? Second question is, how many people have you had come in trying to shove their elbow in their ear? But the idea here is that, what should you be putting in your ear?
Your elbow.
Nothing. Right? Okay? So like those of us who are sitting there digging for gold or whatever, you shouldn't be doing that.
Are these earbuds compliant with that guideline?
Sort of. Technically, AirPods, earbuds, those sorts of things don't go inside the ear canal. They're supposed to stay in the outer ear. Okay?
I mean, there's a little flap holding.
They're little flappy things that seal it off and make the noise and all that kind of stuff. You should be more, so they design those things so that you can't like really shove them in too far. You should be more concerned with how loud they are, which we'll get to in a bit. Okay? All right, so why are we talking about all this? Well, because some of you are like pre-doctors and get excited about this, and the rest of us are like, that's kind of interesting. So, what's the eardrum's job?
Tunnel those sound.
It like wiggles back and forth, doesn't it? Right? The sound waves are coming at you, right? They travel down the ear canal, and then they hit this membrane, right? And so the sound waves are coming in, right? Doing whatever bouncing they're doing, okay? And that causes the eardrum to start to wiggle back and forth. Well, that wiggle in and of itself is pretty small. I mean, there's just not a lot of energy behind that, and moving that membrane, depending on how stiff or sick or whatever it is, can be kind of hard. And so humans evolved, and other mammals evolved, a natural amplification system, there's 3 bones in the inner, hammer, anvil, and stirrup. Did I get it right?
I think it's malus.
Yeah, well, those are the Latin names, but I'm more of a commoner myself. Right, okay? And those 3 bones, they're labeled auditory bones right there, are amplified, that very small wiggle that the eardrum is doing, into a bigger signal. And channels it into the snail that lives in your head. The cochlea. It's not a literal snail, it's just snail shaped, right? And inside the cochlea, lining the walls of the cochlea are little tiny hairs called cilia. And they range in length, some are short, some are long. And each cilia terminates in the wall of the cochlea into a nerve ending. And so a sound comes in and travels into there's fluid inside there that helps to transmit all of this sound. Different wavelengths and frequencies of sound waves will cause different cilia to resonate. We talked about resonance before, where we're pushing a system at the frequency it wants to vibrate at. So longer cilia, they're not literally this long, don't worry, okay? They will vibrate at lower frequencies, whereas shorter cilia will vibrate at higher frequencies. And when each one of those cilia get tickled at the frequency it wants to vibrate at, it sends this nerve signal down to the nerve bundle, which goes into your brain, right? And your brain analyzes that information and tries to make sense of the sound that you heard. I think I just described a miracle. Like literally, like we understand how all of this happens, but the fact that it even functions right most of the time, okay, to me, is absolutely incredible. And it is not surprising to me that it takes kids a while to learn how to talk, right? I mean, how long does it take a kid to really be understanding words and speaking like complete sentences and stuff? 17, 18, right? Like it's like 3, 4 years old, right? Like, I mean, some kids are saying, nah, or, you know, the parents go, oh, that's so cute, right? But it's incredible to me, right, that so much of this works, okay, kind of right out of the gate. But there are situations where it doesn't work. Juan, did you have a question?
So I just was literally looking at the ear yesterday. And so,
In a class or just on your own? Don't answer that question. Go ahead. Okay, all right.
And so what I saw was that I think closer to the opening of the last bone, the hairs are short, or they're stiffer.
Yeah.
Farther in, they're like looser.
Mhm.
Kind of the same thing with like the guitar, like
Yes. Yeah, they're tuned. Those little cilia are tuned to specific frequencies, right? And there's a really fascinating thing that happens, and this is cross-cultural. This is, if there's one thing that unites human beings, this is it. Independent of culture, faith, anything, okay? If you hand an adult a baby, that adult will turn into an idiot. What do I mean? Somebody hands a baby to an adult. What does the adult start doing? Like, what happened? This is a normal functioning adult, and all of a sudden they're doing like boo-boo words, right? When adults talk to each other, what do we sound like? Adults. Boring, right? Okay? We tend to speak in monotones. We tend to speak, and if we're getting really animated, sometimes we'll put our voices up. But most of the time, we're just communicating, hey, what happened, right? We're not varying the pitch of our voices very much. So why is it that any human, when given an infant, will start sending their voice up and down through the pitch range? Oh. What are we doing for that child? We're helping their brain get programmed in the full range that human voices are able to produce. So that they can then start putting together sounds like food, right? You are at the point where food, you don't even think about having to, you know what that word means, right? And what it's associated with, right? But an infant brain doesn't, right? And it takes time to kind of calibrate this whole system and get it working. Now, when the system breaks down, okay, then we've got problems. We've got hearing loss, we've got people from birth that have problems. But depending on the kind of hearing loss that is taking place, we actually now can fix it. The cochlea is where the brain outside world interface is really taking place. The place where a mechanical signal gets turned into an electrical signal in the nerves that goes to the brain. And so, if the hearing loss has been caused by cochlear problems, the cilia are damaged in some way, shape, or form, or stop responding, or any of that kind of stuff, there's implants called cochlear implants that are surgically put into the cochlea that becomes the thing that stimulates the cilia and the nerves. An external hearing aid, okay, so the hearing aid is sitting on the ear of this person right here, and then the implant, the transducers, like a little magnet that sits there, okay, goes to the implant in their ear, and they're able to, the computer listens to the sounds, sends that to the cochlear implant, which can then couple into the nerve pathways that go to the brain. It's actually, it's like we are living in Star Trek. Like seriously, it is amazing, right? What we're able to accomplish. And I want to show you a short snippet of a video. There's a lot of these on YouTube and stuff, but this one was one of my favorites. This is a video of a woman who was born with hearing, had hearing loss, is a kind of early child, and then was getting fitted for her cochlear implant for the first time. So she had had the surgery, and now they're putting the hearing aid and getting the implant right, kind of lined up and calibrated and stuff like that. Her husband is filming the video, okay, and this will be the first time that she hears a human voice in more than 20 years.
It's like so close. There you go.
So that's the technician helping her.
We're not right over it. There you go. It's beeping. So now technically your device is on. Can you tell? Oh, that's exciting. Here, you can put it down for a second. Just get used to the sound. What does it sound like?
I mean, I can't even imagine, right, what it must be like to be able to hear again. This woman had not heard her husband's voice until this day, right? Just absolutely incredible. If we have time in physics, well, you'll get to physics 2B and you'll learn about vision, and we can do kind of very similar things with eyeballs now. Like I said, we are living in Star Trek. It is just absolutely incredible what we're able to pull off when we understand what's going on with these systems. All right, so let's talk about sound levels. So we're going to talk about volume and how loud sounds are and how we measure that. Unfortunately, this is going to take us into the realm of logarithms. So get your log base 10 button ready on your calculator, right? Because sound intensity is measured in a unit that you may have heard before, but doesn't make very much sense. And it's called the decibel. So here's the problem. There is a minimum at which the average human ear is capable of registering a sound. Okay? And that minimum, this will be a number that you're gonna see a lot, okay? 1 times 10 to the minus 12 watts per square meter. Intensity is measured as power per area. I should probably have written that one down. Let's go back. Intensity, I know, it's capital I, I'm sorry, is power per area, right? So we would write that intensity as power per area. And in standard SI units, power is watts and area is meters squared, right? So it's a watt per square meter. And that's the intensity that we need to use if we're like adding intensities together or doing something with combining multiple sounds. But the lowest possible intensity that the average human can hear is defined. It's called the threshold of hearing as 1 times 10 to the minus 12 watts per square meter. Now, on the other end of that, is there a sound that is too loud, so loud you can't hear it? You said yes. Why? Because your like head would explode, right? Like this is energy, right? It's power. It's energy per time, right? And once you exceed a certain level of energy, like things break. Okay. And so we don't define like the loudest possible sound, okay, that would cause like explosions or anything. But instead, we define something called the threshold of pain. And that's how you have to say it. You can't just say threshold of pain. You have to say threshold of pain. Right? That intensity is 1 watt per square meter. So if I were to take a sound and send it out at 1 watt per square meter to you, what you would experience would be the pain reflex, is what we call it. You would probably move to cover your ears or to turn your head away. There would be some aversion, okay, to the sound that you are experiencing. So how many powers of 10 are there between the lowest possible intensity we can hear and where we go, ouch? It's 12 powers of 10. That's, so 10 to the 9 is a billion. What's 10 to the 12? It's a trillion. So there's a trillion times difference between threshold of hearing and threshold of pain, right? Which is why the decibel scale was brought in. What the decibel scale does is it takes that huge range and compresses it down into a much smaller range. That's actually what logarithms do. They take big numbers and make them small. So here is a table roughly of the kinds of intensities that you would maybe hear on a regular basis, right? So threshold of hearing, notice, is at 0 decibels. And we're going to talk about how we calculate these numbers in just a minute, right? So 0 decibels is being able to just barely hear a sound. I didn't know what that meant for the longest time, and so I went and found the acoustical physicists in graduate school, the graduate students that were studying all this stuff. And I pulled one of them aside and I said, look, what is the threshold of hearing? Like, do you have, beyond the definition of the number, like, is there a situation that I could experience, right, where it would be like, I could just barely hear it? And she looked at me and she said, yeah, we actually have an example of that. And she said, imagine that you are alone in a forest. I was like, wait a second, I've heard this joke. She said, no, it's not that joke, right? Imagine you're alone in a forest and there's no wind, right? So there's like no rustling sound, there's no animal sounds, like that kind of stuff. It's perfectly still. And you're standing under a tree and a leaf like falls from the tree and lands on the ground next to you. Technically 1 meter from your ear, but it's okay, right? The sound of that leaf striking the forest floor is 0 decibels, or the threshold of hearing. That very faint touch, right? I was like, okay, that's kind of interesting. But as you can see, right, normal conversation, which is not what we're having right now, because I'm not speaking with you face to face, I'm projecting my voice out into the thing, right? They don't have lecture on here, but it's probably beyond the threshold of pain. No, that's mental pain, that's not physical. Well, sometimes it's physical pain, I guess, right? But normal conversation, 60 vacuum cleaner, you kind of get an idea. But look at that. Siren or rock concert is at 120 decibels. 120 decibels is the threshold of pain. It's the threshold of like aversion, right? If you're standing right next to a siren, you're probably going to cover your ears. If you're going to a concert, a lot of times concerts, depending on how far away from the speaker you are, will be 140 decibels. So that's why they tend to try to put distance between the speakers and the people in the audience. Try and get that sound. Intensity does fall off with distance. And we'll get into that in a second. But the tricky thing about a decibel scale is it's not linear in the way that our brains like to interpret things. For example, let's take a look at this whisper, okay? 30 decibels, right? If we go from 30 decibels whispering to mosquito annoyingly buzzing in your ear at 40 decibels, that is a 10 times increase in the intensity level of the sound. A mosquito is 10 times louder or more intense than a whisper. But if we go from whisper to normal conversation, do you see how whisper is 30 and normal conversation is 60? That's 10,000, I had to count it because it's not linear. That's 10,000 times more intense. What's going on here? If we have a sound at 30 decibels and we have another sound at 40 decibels, that's a 10 times increase in the intensity. This is how logarithms work. A 50 decibel sound, how many times more powerful is a 50 decibel sound compared to a 40 decibel sound? It's also 10. Okay? How many times more powerful is it than a 30 decibel sound? 10 times 10, which is what? 100. And then a 60 decibel sound, see, I was off by my powers of 10s. A 60 decibel sound is 10 times more powerful than a 50, right? But it's a 10 times 10, which is 100, times 10, which is, what's 100 times 10? 1,000, right? Times more powerful. So a logarithmic scale messes with our brains. From the threshold of hearing to the threshold of pain is 1 trillion times more intense. Again, those powers of 10 that are in there. Just so you know, this might look confusing, but if you ever go get your hearing checked, this is what they're trying to find out. Our ability to register sounds and to hear them, that threshold of hearing, is frequency dependent. In other words, we're not great at hearing low frequencies. Low frequencies need to be louder for us to perceive them. And same thing goes for high frequencies. So there's an envelope. This threshold of hearing is actually curved. And it's right around like 2,000-3,000 hertz that were actually the best. The sound level doesn't need to be as high for us to hear it, okay? But as we get down into the low frequencies, we do need a little bit more intensity. And by the way, 100 to 1,000 is roughly music. Some exceptions there, but that's what we're used to. Okay, so let's go back and let's talk about using decibels, okay? So I'm just gonna repeat, right? Intensity is power per area measured in watts per square. Whoa, come back here. That's a definition, and that's intensity will be used for light in physics 2B, and that's general. Okay, that's not just sound. So how do you get more intensity? What are the two things you can change? Power. So how do you change the power? More energy, less time. right? Because power is energy divided by time. The other thing we can mess with is area. And if we want intensity to be big, what do we want area to be? Big or small? It's in the denominator, right? So the smaller area gets, the more intense. In other words, if you take a very energetic sound and you focus it down into smaller and smaller area, you're making it more intense, right? So there's kind of a trade-off there. But to overcome this problem where our reference intensity or our threshold of hearing is 1 trillion times smaller than when we go ouch, we've developed this decibel scale. And back in chapter 1, we did unit conversion. Right, we learned how to convert units back and forth, and we have those conversion factors, right, that we set up fractions and multiplied by. The decibel scale does not have a conversion factor. It has a conversion equation. You have to use an equation to convert to decibels and back again. So a decibel is 10, that's the Greek letter beta, by the way. 10 log, whatever the intensity of the sound is, divided by the reference intensity. So if you have a sound in watts per square meter, you can then convert this into decibels. We use the symbol dB, d beta, for this. So this equation gets you put in watts per square meter into this equation, and what you get out are decibels. The reverse of this equation, the way you get to the other side, is that if you want to find the intensity in watts per square meter, you take the reference intensity and then you put the decibel level as a power of 10 divided by 10. So this one will take you from a decibel and give you out watts per square meter. So those two equations in the box are how we get back and forth between intensity in watts per square meter and the intensity as measured in decibels. And you might be like, well, why bother? Why even go out on watts per square meter? Writing lots of zeros and lots of scientific notation can get cumbersome. And so that's why the decibel scale exists. But it's further complicated in that there's really 3 decibel scales out there. I'm talking about the scientific decibel scale. Audio engineers that either are doing audio for music or Hollywood, movies, TV, that kind of stuff, they have a separate decibel scale. And if you've ever done any kind of audio recording or used like a microphone, mixer board, or any of that kind of stuff, you've probably seen the scale where 0 is like sort of towards the top end, and then there's like negative decibel levels that go quieter, and anything over 0 is a positive, and there's probably like a green, yellow, and red signal. What they're doing as audio engineers is they're trying to hit a certain volume, a reference volume, and so they'll go into like negative decibels for quiet sounds and positive decibels for loud sounds. They're just kind of arguing where 0 is. The third one is another audio recording one that I don't quite understand that reverses that whole thing. Anyway, there's different ways of thinking about sound intensity. When you're recording sound, you want to make sure that you don't get distortion. You've probably experienced a distorted audio signal sometimes. It sounds like blown out and you can't understand what the person's saying because it's like the microphone is too loud, okay? So an audio engineer is trying to find in the range of sound that's being produced by the recording, where's like that middle, or where are most of the sound intensity so that we don't blow it out, but we also don't make it too quiet. My brother-in-law works in the visual effects industry, and we were down at his house Thanksgiving one time, and one of his friends is an audio engineer and did the audio engineering for the movie Ender's Game. And he and I like ignored everybody for 2 hours and just geeked out on decibel scales and that kind of stuff. And I took him to task for his weird decibel scales, and he made rude comments about physics. And we had a lot of fun. It was good. Anyway, let's do an example of working our way through, right? Being able to work back and forth in decibels and why we would have to do it, okay? This is a very common situation to take place where instead of just having one sound, there are multiple sounds. I think the chemists were out there making noise in the hallway just a few minutes ago, right? And I had to compete with the sound. And the competition was, right, what you're hearing behind you versus what's in front of you. And I had to raise my voice in order to maintain your attention and override the signal of what was going on out there, right? So you've never had this experience, right? Where you're sitting there trying to enjoy whatever it is you're watching on your device, and somebody else comes along, and this person is probably has some sort of authority over you, right? Mom, dad, boyfriend, girlfriend, dog, somebody, right? And is getting you to do something, okay? So you're listening to a sound at 50 decibels, and somebody comes along and starts talking at you at 70 decibels. What we're going to do is we're going to find the total intensity in both watts per square meter and decibels. But the key takeaway here is that the sound that you hear is not 120 decibels. You can't add decibels together ever. They don't add the way that you think. The decibel scale isn't linear and doesn't follow the math that we are most familiar with. So, to be safe and not have to learn how logarithmic scales work, always, always, always convert a sound intensity into watts per square meter, do whatever you're being told to do, add it together, multiply, whatever, and then if they want the answer in decibels, convert back. So first step in this problem, before we can go add these sounds together, is we have to convert from decibels into watts per square meter. We're going to use this one. The second one I gave you, right? Because we want it in watts per square meter. So this reference intensity is 1 times 10 to the minus 12. And then that's 10. And for the 50 decibel sound, that would be 50 divided by 10. Well, what's 50 divided by 10? It's 5, right? Okay. If you have a 56 decibel sound, just do it in your calculator. 10 to the 5.6, just do that in your calculator, right? I rounded these so that it would be, what's minus 12 plus 5? It's minus 7, isn't it? So I'm just using the rules of exponents, right? To work my way through it because it's pretty easy. Okay, so there we go. That sound, the 50 decibel sound, has an intensity of 10 to the minus 7 watts per square meter. Okay, we can do the same thing with the 70 decibel sound. Minus 12, 10 to the 70 over 10. Minus 12. By the way, 10 to the minus 12 is a shorthand notation for 1 times 10 to the minus 12. That's why, because 1 times anything is still the same thing. 10 to the 7, that's going to be 10 to the minus 5, isn't it? All right. So now what we need to do, the problem is asking us the total intensity. So I'm going to add my 50 decibel intensity and my 70 decibel intensity together, but I'm going to do it in watts per square meter. So 10 to the minus 7 plus 10 to the minus 5. And when I do that, I get 1.01 times 10 to the minus 5 watts per square meter. So there is my total sound intensity in watts per square meter. So I've answered that part of the question. Find the total intensity in watts per square meter. There it is. But what is that in decibels, right? Like that decibel level, what's the combined sound then? Before we do the calculation, does anybody wish to guess? I mean, just take a guess. We're not gambling here. There's nothing on the line. But what's the decibel level, do you think, if a 50 and a 70 decibel sound get together? 100? 120? It's not 120, I already said that.
90.
90? 50? Like barely changes? To get back to the decibel, it's going to be 10 times the log of our intensity in watts per square meter divided by the threshold intensity. That's 10 log 1.01 times 10 to the minus 5 all over 1 times 10 to the minus 12. And putting all that into the calculator, and I can't do this in my head, right? Okay, you gotta use the calculator. This number turns out to be 70.04 decibels. What happened? How many times more powerful is your mom's voice than your computer? If your computer's 50, it's 100 times more intense, 100 times more powerful. And so is it any surprise that the 50 decibel sound loses? Right? Like it barely notches up the 70, right? We add, this is the weirdness of a decibel scale. It doesn't behave the way you think it does. And so always, always, always get into watts per square meter, and then do whatever you're being asked to do, add sound, you don't really subtract sound, okay? And then get back into decibels. Whatever you do, don't manipulate, add, subtract, multiply, divide in decibels. It's just not gonna be what you think it is. All right, so, excuse me, the takeaway here, right, is that there are these conversion equations for getting between decibels and watts per square meter. It's not a conversion factor, it's not a linear thing. It's an equation that is necessary to get back and forth between them. Okay. Last thing in chapter 16, so I'll do this now, I'll probably run out of time, and so chapter 17 is going to start tomorrow, right, in your respective lab sections. Doppler effect. This is a change in frequency because a sound is moving. Well, either the source is moving or the person listening to it is moving, or both. So let me demonstrate the Doppler effect for you, and then we'll get into why it's kind of fun. All right, so I've got inside of this football-shaped thing on a string a very annoying buzzer, right? Does anybody want to give me money to turn it off? No? But that sound, right, is just a single tone, right, coming out of the speaker that's inside of this football. What I'm going to do, I'm going to turn that on and I'm going to spin this around my head, okay? And I want you to listen to how the tone changes simply because it's moving. What happened? Wow, good, yeah, right? Okay? The frequency changed. As the football came towards you, the frequency was higher. And then as it sped away from you, it went lower. The Doppler effect is that shift in frequency. Was the frequency of this speaker changing? No, it was emitting the same sound. But you heard a different frequency based on the relative motion of the source. You've experienced this as a Fresno City College student. The train comes rumbling down the tracks, right? It's blowing its horn. The horn sounds a higher frequency when it's coming towards you versus when it's past you and the frequency goes down. There seems to be a lot of cars on Blackstone McKinley that have muffler problems because they're right, big loud cars, and you hear it as the car goes by, right? It's It's kind of this. You really got to practice that, by the way. Don't try that one at home, okay? That shift, okay, as the sound source goes by, as it moves from coming towards you to then transitioning to moving away from you. Higher frequency coming towards you, lower frequency heading away. I've got a very basic animation here. So this is a sound source, a trumpet in this case, and somebody listening to it. And if nothing's moving, we have a nice even set of sound waves coming off of this thing. Everything's fine, okay? But if we put the trumpet in motion, look at what's happening on the front compared to the back. As this source of sound moves, it's compressing the wave fronts in front of the motion and causing the wave fronts to spread out in the back. And as we push wavelengths smaller, frequency goes up. Remember, speed stays the same as long as we're not changing the medium. So that person is going to hear a higher frequency as that trumpet comes towards them. If we reverse it and we send the trumpet away, then the wavelengths are spread out there, right? They're smooshed together in the direction of motion, but moving away from the observer, we get that spreading out, which is a lower frequency. So the Doppler effect is a mathematical description of the frequency shift that takes place, depending on whether or not something is moving towards or away from another object. And this is another part where Mr. Balogh does something different from your book. I know it's annoying, but I truly feel, in my professional opinion, that the way I do it is better. Okay? A lot of YouTubes, a lot of books, a lot of written material, you'll get to the section on the Doppler effect, and all of a sudden you'll have like 4 to 8 equations, depending on who's doing the writing. And what is going on here, right? I believe in one equation to rule them all, right? And in the darkness, if I can simplify, if I can bring my model down to a common language, I'm going to do it instead of having all of these like caveats and things like that. So what I do, and I have seen this done by other physicists, this isn't just my idea, okay? But all Doppler effect equations usually have like frequency of the observer. This is what we're solving for, okay? And then we have the frequency of the source, the thing that's making the sound, the frequency we're listening to, multiplied by a fraction, okay? And this fraction, this is where I'm going to deviate from your book, okay? I'm going to put v plus the velocity of the observer over v minus the velocity of the source. Again, different people will treat this differently. They'll write this as v plus or minus VO all over v minus plus VO. This is the other sort of common version that I've seen. I don't like this one either, because what the heck is a plus minus and a minus plus? Really, what's going on there, right? So again, I'm just pointing out to the fact, right? There's different ways of doing this. I personally feel like this is the easiest. Now, this equation does come with a little mini spreadsheet. Don't worry, it's not a hard one, okay? For me, the little mini spreadsheet's important because it's visual, and I'm a very visual learner, and I need to kind of see it. But there's a rule that you want to apply when you're using the equation in this form, okay? And that's velocity, okay, is positive if something is moving towards, and velocity is negative if moving away. That's the rule. I usually do this. I'll say velocity of the observer, velocity of the source, and then I'll come along and I'll make a little tiny spreadsheet, okay? And I'll go towards and away, and if it's towards, it gets pluses, and away, it gets minuses. I just kind of have that picture in my brain, right? But if words work for you, fantastic. Away is negative, towards is positive. Yeah, okay, good, right? Towards and away from what? The answer is yes. If a source of sound is moving towards an observer, it's plus. If the observer is in motion and is moving towards the source, it's also plus. The Doppler effect has to do with relative velocities. And where some of the treatments and books and things get really into relative velocity, we are not going to concern ourselves with situations where there's like any kinds of angles of approach or any of that kind of stuff. What we're doing is just something like in a line. It's coming towards you and then it's passing you, or it's doing something, right? Okay? We're not going to worry about relative velocity directions and things like that. So with those two things in place, you can do any Doppler effect problem. Your book would suggest, I think, that there's 2 or 4 equations that have to apply in different situations. This equation applies to every situation. Situations where the observer isn't moving. Maybe you're standing on the side of the road and a siren is coming at you or away from you, right? What would you put in for the velocity of the observer if they're not moving? 0. You just put 0, right? Okay. What if the source isn't moving and you're running towards it? What do you put in velocity of the source? 0. They're not moving, right? Okay, so, and if you're both moving in the same direction, well, let's talk about all those different relative velocities. So I've got a problem here that I am going to do 4 times. There's 4 possible situations for the Doppler effect in one dimension. Okay? I'm going to calculate every single possibility for an ambulance moving towards or away from us, depending on the direction it's traveling and where it is. You're like, Mr. Bailey, it seems like there's more than 4 of those situations. Nope, there's only 4. Let me show you what I mean. So case A. It's possible, okay? And in all these cases, we will be moving north, say on Highway 41 or something, right? We're driving up, okay, north, okay? So here's the observer. It could be that the source is in front of us moving in the opposite direction. Or keeping the same direction of our motion and the same direction of the source's motion, the source could have passed us and be behind us. So that's a case where we haven't changed the direction of these velocities at all. We simply changed the relative location of where the objects are. A third possibility would be we are moving north, and the source is also moving north, but is behind us. And anybody want to take a guess as to what the fourth possibility is? Same direction, but is now past us, right? So we're still moving north, and this thing has now passed us. Now, and you might be like, well, but Mr. Balogh, what if we're traveling south, right? Aren't there 4 more situations? No, there aren't. Because I could flip our direction and end up with exactly the same 4 situations where our velocities are anti-parallel, we're behind, or parallel, and it actually doesn't matter. As long as we're all pointing in the same directions or opposite directions, we will only have these 4 cases. Okay, so how would I calculate this for A? The frequency we hear is equal to the frequency of the source times v plus the velocity of the observer all over v minus the velocity of the source. So what numbers do we put in? What's the frequency of the source? 2500, right? 2,500 hertz. Okay, v in this equation is the speed of sound in air. What is the speed of sound in air, if we're not told? 343. So we're going to do 343 plus, and then we're going to write some parentheses. And on the bottom, we're going to do 343 minus, and then we're going to put some parentheses, and we're going to come back in here. And this is where we are going to put a direction on a number. We're going to look first at the velocity of the observer. Is the observer moving towards or away? Is the orientation and direction of the observer pointed towards or away from the source? The observer is pointing up, right? The source is up here. The observer is trying to get towards the source. So according to the rule, or according to my little tiny spreadsheet, what sign do we put on something that's trying to move towards the other thing? Positive. So I'm going to put in positive 25. That's the velocity of the speed of the source, and the positive sign is its direction. Okay, the ambulance. In case A, is the ambulance trying to move towards or away from the observer? Towards, right? It's in front, it's pointed down, right? It's trying to get, again, closer, it's moving closer to the observer. So that's towards, and I'm going to put in positive again for the 40. Now notice, right? A positive and a positive on the top doesn't do anything, but I have a 343 minus a positive 40. That's the same as 343 minus 40, right? Okay. So we do all that, we do some calculate, we put in our calculator through 3040 hertz. Okay, so what happened there? Is that frequency bigger or smaller than the original frequency? Bigger. Do we expect it to be bigger? What does the Doppler effect tell us about this, a sound that's coming towards you? It gets a higher pitch, okay? So we'd expect a higher number. All right. Now we have case B. We're still gonna, we need the 2500 on the front. 343 plus all over 343 minus. Okay. Is the observer moving towards or away from the source in case B? It's moving away. You see how it's pointed away from the source now? Because the source is past it. So what are we going to put on the velocity if it's moving away? Negative sign. Minus 25. And then the source, what is it doing? Pointed towards or away? Also away, so minus 40. And now notice, right? A positive and a negative on the top means it's 343 minus 25 in the calculator. But on the bottom, what's going to happen?
Addition.
Yeah, the negative and negative becomes a positive, doesn't it? So mind your signs. And here we get 2080 hertz, which is lower than the original sound, which is what I expect, right? As two objects move away from each other, the frequency should go down. Case C. 2500, 343 plus, 343 minus, and we'll go ahead and insert. Okay. Is the observer in case B, go ahead.
Why is 2500 on this one if the source is faced up?
The frequency of the source doesn't matter on direction. The direction doesn't matter. Yeah, it's just the frequency of the source. In this case, 2500 hertz. Good question. Okay, in case C, is this observer moving towards or away from the source? I mean, I know, like, if we're going at 25 and something's coming up behind us at 40, we're getting closer together, right? But what are we trying to do? What is our direction compared to where the source is? Towards or away? It's away, right? We're pointed away from the source, okay? And so, away is a negative velocity. But what is the source doing? It's going towards, right? It's pointed towards the observer, so we'll put positive 40. We'll get that in our calculator, 2620. It's slightly higher, but not as high as if we were approaching each other at much faster relative speed. And finally, 2500, 343 plus, 343 minus. Okay, in the blue case down here, case D, is the observer moving towards or away from the source? It's trying to get towards it. We're getting further and further behind, but that doesn't matter. The equation is going to handle that. We're trying to go towards it, so positive 25. And what is the ambulance doing? It's pointed away, so minus 40, which would give us 2400 hertz. So in both the green and the blue, there was a shift, right, higher and lower. It just wasn't as big because the relative speeds were different, okay? But there's still a Doppler effect that happens there. And ran out of time to talk about applications of the Doppler effect. One of the coolest things is ultrasound, Doppler ultrasound, where they use the Doppler effect to measure blood flow in veins and arteries for diagnostics. I will see you tomorrow where we will do probably more than half of chapter 17.